I hope I didn't scare away too many of you with this title, Universal Points in the Asymptotic Spectrum of Tensors. But this is the title that sort of best describes the work from a historic perspective. It's joint work with Peter Frana from Budapest and Jeroen Zoutam from Amsterdam, and you can find it here on the archive. In the realm of quantum information theory, I could have given a slightly different title, not as precise, but let me do it. It's additive slug monotones. So that could be an alternative title. Probably some of you are more familiar with the words here, entanglement monotones, and then it's not LOCC monotones, but SLOCC monotones. But I will sort of like come to that later. The subject of this talk sort of starts really in the 1980s historically. Volker Strassen built what we would now call a resource theory of tensors. And let me just say from the outset, I think it is, among all resource theories that I've seen in quantum information theory, it is the sort of like most developed and most articulate, and it contains a number of statements of which I think in many other resource theories we look at, we have no idea that something like that could even exist. So I've become very fascinated with tensors and this particular resource theory. I want to share a few things with you about it. And so Strassen was interested in these tensors coming from a problem in complexity theory, actually algebraic complexity theory, so not working with bits and bytes, but with working with variables, and in particular the problem of matrix multiplication. So there's a complication to this talk. That's this blackboard. I'll have to learn. Oh, shit, that was the wrong one. Okay, sorry, that was the wrong one. Okay, so that will happen probably many times. So yes, so that's 1980s. That's Volker Strassen. And so there's matrix multiplication. What is matrix multiplication? Well, we all know how to multiply two matrices. Let's say these are n by n matrices with some entries here. And if we multiply two of such matrices, then how are we going to do it? Well, we are going to take the, say, the ith, right? We're going to take the ith row and then the jth column, right? So that's the ith row and say the jth column, and it's going to produce, we're going to take this one here, we multiply it with this, and we're going to produce this element in our matrix over here, right? And more generally, we'll then later produce all the elements. So what is the runtime of this algorithm? If I just, for the moment, only count multiplications, we could also count additions, but it will not make a difference. So if we count multiplications, and maybe I should really have left it down there. Well, sorry guys, I'm confused about this. Okay. Then the complexity of this problem is actually order n cubed, because I have n square outputs, and for each of the outputs here, I'll have to do this row by column, which needs n multiplications. So if I count the multiplications, my algorithm will need n times n squared, that's n cubed. And so Strassen, the whole story starts with Strassen trying to prove this is optimal. And actually he didn't succeed in proving it's optimal, but instead he delivered an algorithm that was actually beating n cubed. And at the moment, well, there's a lower bound n square, which you can basically see because the output has, you have to touch all the variables. And so that roughly gives you a lower bound of n squared. We actually don't know the answer yet. So the coefficient here is called omega. That's called the matrix multiplication exponent. And Strassen, with his rather ingenious algorithm, first showed that it is smaller than log 2 of 7. That's around 2.8. And the current record stands at 2.38. And people have even worked out higher digits. But it's still open what the best lower bound is. So we don't know what omega is. We just have these developments that have. And actually, one of the developments is related to this theory that I'm presenting today, which is also due to Strassen. But how is all this related to my title and to tensors? Well, if you look at the operation that we have to do here, you see that matrix multiplication is a bilinear operation. It takes a matrix from here and a matrix from here, and it's linear in both of these operations. So it's a bilinear map with a matrix-valued output. And now you can imagine that if you take the dual of the output, then what you get is actually a trilinear function into the complex numbers. And well, how can you represent a trilinear function in the complex numbers? Well, one way of representing this would be to actually put it into this space, right? So there could be some, I like to call this trilinear function, actually we call it MAMU n. So MAMU n for matrix multiplication is this function in here, and that is what is called the matrix multiplication tensor. But Strassen then from this, because in this whole attempt to lower this here, there come other questions, other tensors come up, and other questions about transforming them and so on, and that motivated him to study just a general tensor, so an element in here. And you know I'm from quantum information, of course. I already suggestively write this as a psi, because of course an element in this space, or more generally for us now, we will not look at Cn, we will look at CD tensor, CD tensor, CD. Of course, that's a quantum state, right, of which we may have forgotten the normalization. The normalization is not so essential here, and therefore, in tradition with the literature, I'll call it a tensor rather than a quantum state. Yes, Ashwin?
What's the notion of duality that you're using here? So what's the dual of that bilinear map?
Well, I mean, just take this here, right, and then you're in a product. I mean, you're in a product with itself, with the dual of this space, right? This is a map from. So if you know, this is an endomorphism, right? From here to right from this to this, right? And then you just take the dual of this space, and then you're there. Yeah, so it's a trilinear map, right?
No, I understand. I mean,
yeah, it's a.
That map was, you were looking at it, I was wondering what the notion of duality is.
Yes, but just normal matrix duality.
Yeah.
Okay. Well, what is sort of like a good to do for the moment is also to introduce some notation, and maybe this is also why people. I'm going to try to use quantum notation as much as I can in the talk. So this is a computational basis, and I write down the tensor in its basis notation. Let me give you some examples, and maybe just like just an example with dimension 2. Our favorite example, of course, is the GHZ state. You see, I'm going more and more into quantum slang here, right? That's a GHZ state. That's, of course, an example of a tensor. If you think of it as this, as a cube, if you think of these numbers here as a cube, it has a diagonal, right? It's a diagonal 1, 1 in this cube. Then, of course, there's another famous tensor that is 0, 0, 1 plus 0, 1, 0 plus 1, 0, 0. that is known as the W state. This here is the GHZ state. I indicate that the GHZ here has two levels with the little 2 down there. These are two nice examples of tensors that actually, you know, play a very big role in this theory. So it goes all the way up now. Okay, very good. And there's the next one. So there's another one. Maybe you haven't really thought about MAMU. I'm just going to write it down for you. I kind of like defined it up there in an implicit way. But in the quantum information language, you can convince yourself that it looks like this. Right? And if we, yeah, so that's our MAMU. You see that it's like the matrix comes in with I and j, and then it's going to be contracted with j and k on the other one here, and then I get the output which corresponds to the elements ki. Right? Why you know this? You've seen this thing before. Well, that's just 3 EPR pairs, right? In a circle, right? So I have a pair I, right? J, K, K. So you know, in some tensor network, you can think of this, or you can you know, I don't know. It's sort of very funny. And depending on what the dimension, of course, is, if you go from 1 to n here, then maybe it has a dimension n here, which some people call bond dimension. Right, so that's our MAMU. And we want to study the interconversion. We want to think of these tensors. If we're in quantum information, we think of them like as having certain entanglement properties and maybe as a resource. But in computational complexity, also these tensors, they are a resource because they kind of like count how expensive things are, and especially this GHZ state has this role. So Strassen made a definition, and this definition introduced an order of tensors. So we're going to say psi is better than phi, or psi restricts. It restricts to, psi restricts to phi if there exists matrices A, B, C. They are now D by D matrices. So if my tensor, they live in CD, 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 but the dimension is not so important, such that A tensor B, tensor C applied on psi is phi. Right? If by local linear operations I can transform psi into phi, I say psi bigger or equal to phi. Very natural. In quantum information speak, this means psi can be converted to phi by slog transformations. Okay? And in this context, this was first considered by Vidal-Sirac around 2000. So I will stick with the 1980 notation of restriction. Sorry? Yes, so in LOCC, basically what one can notice that in LOCC you have these protocols, right, that are trying to convert something, and they consist of like local operations and then classical communication. Now if you allow post-selection, so if you allow the communicating parties to say the transformation succeeded, if with some non-zero probability they succeeded, it turns out actually that, that it reduces to them just applying local cross operators, okay? To just a single local cross operator. And these are the cross operators, A, B, and C. And so they're somehow not normalized. You see the whole normalization kind of like, it doesn't matter here because of this stochastic in SLOCC. Right, so you can think of them as cross operators. Then, of course, we might kind of introduce an equivalence relation. We might say psi is equivalent to phi if this goes in both directions. So if phi is bigger than psi and if psi is bigger than phi, right? This is sort of like would be a very natural equivalence relation. We don't want to do this very much, but just to mention, of course, this here is equivalent to these matrices then being invertible, and then one can classify all the states or all the tensors that are equivalent under this class of operations. And I think this is sort of what de Vidal-Sirac have done in this example of dimension 2, so C2, C2, C2. And I just want to tell you this classification. So they lump into orbits, you may say, according to this equivalence relations, and these orbits are related with help of this restriction order. So of course one of the states is the GHZ state, and we have other states. I'm suggesting writing it lower. The W state. Let's start with the W state. The W state nicely restricts to, of course, an EPR pair. All right. So what I can do with the W state is I can well, maybe it's more obvious to see that, well, that the W state, right, is 0, 0, 1 plus 0, 1, 0 plus 1, 0, 0. If I now let the third party project onto 0, then I get these two components, and I do a bit flip, and the 0, 1 plus 1, 0 transforms into 0, 0 plus 1, 1. So it restricts to this, and it will also restrict to the other symmetric versions of this. Okay, so it will restrict to 0, 0, 0 plus 1, 0, 1, for instance, and of course 2, 0, and then 0, 0 plus 1, 1. Okay. Wow, so then of course all of this here, if now the third party here projects onto the 0, only the 0, 0, 0 is left, and so all of them will restrict to the 0, 0, 0. Okay, question now, what happens? Of course, I can restrict from the GHZ to this one here. How do I do that? Well, I take a Hadamard, say, on the first qubit, and then I measure, I project onto the 0, and then I'll end up with this state here. It's less obvious to see if this is possible, and in fact, this is not possible as restriction. So I want to just briefly mention a slight generalization of this here, which is called degeneration, where you allow here for all epsilon bigger than 0, there exist these matrices such that here in some norm that you choose, you get an epsilon approximation. Okay, so somehow the property of restriction is not closed in an algebraic geometric sense, but you can close it off with this degeneration. And it turns out actually that the GHZ in this sense is more powerful than a W state because it degenerates to it. But neither of them restrict to each other. So this is the Vidal-Sirac hierarchy, and for 2 qubits. I want to present, if someone is interested, I can later on explain it to you. I did it in my lectures I gave in October here. But I want to give you another example, namely that's the example of Strassen, which I like very much, because of course he was interested in MAMU, right? But he had of course full grasp of resource theory, so he was going to ask how much GHZ can I distill from this? And he showed that he can degenerate to a GHZ of level 3, and you can try yourself. It's a non-trivial result. He also showed, and this was his breakthrough, that that the GHZ of level 7 restricts to the MAMU. Okay, this is what gives you the omegas. What gives you the algorithm. I cannot give you the details now, but this is what gives you the log 2 of 7 algorithm for matrix multiplication. That is really this result here.
Can you explain how you go from this to a better algorithm
for matrix multiplication? Well, the algorithm of matrix. So this here is an algorithm for 2 by 2 matrix multiplication with 7 multiplications instead of 8. Because somehow the GHZ, the number of So if you can write the matrix multiplication tensor as a number of product components, or as a number of product components, then each of these product tensors, they correspond to having to execute one multiplication. Okay, so this one here tells you that you can represent the 2 by 2 matrix multiplication with help of 7 multiplications. Okay, so you can solve this with 7 multiplications. That's a 2 by 2 problem. But then it turns out this works also for if you, instead of the numbers that you have in your 2 by 2 matrix, you put matrices in. Okay, and then you recurse. Okay, and so it shows up in the exponent. So you first take your gigantic matrix, you make it into blocks of half the size, and then you continue. So.
But yes, here you don't assume that the size of the systems are identical from left to right when you restrict them.
That's right, yes. So if you're in doubt, just take the dimension large enough so that both of your tensors live there, and then we consider the notions. Okay. Right, so the GZ is our unit resource, right? Very natural from a quantum information point of view. Therefore, it's also called the unit tensor, maybe. And this, of course, is the size that you have here is somehow corresponding to the distillable entanglement cost, and this corresponds to the distillable entanglement in a one-shot setting, right? And the next thing that the next thing that, of course, we would want to ask is, what about the asymptotics? And there comes Strassen along, and he's going to say, well, I have asymptotic restriction from psi to phi if I can take many copies of my tensor and I can restrict to many copies of this. So it's just an asymptotic information theoretic version of it, and it turns out to be a weaker notion. So sometimes when this cannot be attained, this can be obtained. Okay. Well, it's natural from our point of view. Maybe I should make it formal, to define like an entanglement cost in this setting, right? So the entanglement cost in that setting would be the infimum over R, such that the GHZ of two levels, tensor R times n, restricts to phi tensor n. And so it's the smallest R, the smallest rate, and then I have the distillable entanglement of psi, so is the supremum over R such that psi tensor n restricts to the GZ of 2 tensor R times n. Okay, so these are completely analogous to our setting. And Strassen has a number of theorems about these objects, more than I would be able to present. For instance, he shows that what I alluded to already in the after Fernando's question, I mentioned this with the algorithm, and here he shows that omega is actually equal to the entanglement cost of this. And this is, of course, I mean, we know this has to be bigger than the distillable entanglement. And this is, of course, fun. He shows this too. Okay, if you think about it, it shows that that this MAMO I can convert to asymptotically to GHZ states. This is a non-trivial protocol that he showed the existence of. And that was one of them leading to improvements on the matrix multiplication exponent. What is interesting in this whole subject is that much more is known about the distillation task than about the cost task, which is kind of like opposite to what we know in entanglement theory. There we know much more about the cost task than about the distillation task.
So who is this theorem due to?
This is due to Strassen. I think I'll only mention theorems due to him today. Well, he has a more fun theorem, which is sort of like bringing us closer to the title. Namely, he shows that this asymptotic restriction here can be decided with help of additive entanglement measures. So he shows, well, he shows there exists a compact Hausdorff space worth of functions with the following property, So, you know, I just say there exists a set of functions, okay, which you call functionals, set of functionals, E. They go from the tensors, I make it a little bit informal, into the positive numbers that have a bunch of properties, namely that psi tensor phi, well, they're multiplicative, okay, or they're additive, sorry. They have tons of other properties too, but for the moment I only want to show you this property. They're of course normalized, so if you plug in the GHZ state, they normalize to log R, and well, meaning that if actually it's enough to do it for the 2, right? It normalizes to 1 if I do it for the GHZ2. And they are monotone under the normal restriction, so they're monotone, so this is bigger than phi, you know, if psi restricts to phi. So, so he shows there exist these functions, okay, with the following thing, right? So this was not the statement yet. That was just the object that should exist, such that for all E in this set, okay, so you have this set of E, okay? And for this set of E, if for all of these functions, E of psi is bigger than E of phi, then psi asymptotically restricts to phi, and conversely, okay? So one direction is easy, so this is like the easy direction. Well, because if this asymptotically restricts to phi, then of course, if I take n copies, this restricts to this. And now if I apply my function to it, all right, because the function here, these additive monotones, they have this property. So I have this property, but because they're also additive, all right, because they're additive, this gives me n times this. And because this is additive, well, n plus little o of n, E of psi, right? So this was the easy direction, and this is sort of like the hardcore direction using some generalization of Stone theorems that go a little bit off here. The monotones have also more properties, but I find it remarkable because they have this additivity property. We know they exist, and Strassen couldn't write down a single one of them. Okay, so he showed they existed. Well, there's some trivial ones, but he showed they existed. But he also showed that his theory applies to subclasses of tensors that are closed under tensor product and direct sum, especially a class of tensors called tight tensors. And actually, matrix multiplication, the GHZ state, and others, they're examples of tight tensors. So he found this important class, and on this class of tensors, the same theorem holds, and there he produced the functions. Okay, so he produced not necessarily all functions, that's not known, but he produced a whole simplex full of functions.
So apart from this, in like log monotones, I know Schmidt rank is one. It's not log Schmidt rank is not additive, but at least it's log monotone, right?
Yes, yes.
Is there any other that we did before? I only know.
No, I don't think there was any. Well, you can do some local dimension. So local dimension, so you can do something with the format of the tensor. We call it the format. So the local dimensions, you can do something with this. But apart from that, I think nothing. I mean, you can a little bit play with the local format, but that's it. And Strassen did that, but there was nothing known. So well, so that sort of brings me. It's 1:15, right? I have time to 1:15. So that brings me to our results. So so we have a definition of functions. So we index them by a parameter theta, which I'll say in a moment about. And the functions are defined as the infimum over psi restricts to phi. Degenerates. And then this is basically like an averaging of the local entropies of the local reduced density matrices. Oh, that's 2. Okay, so just imagine you're going to take your psi, right? Then you're looking in your entire slug orbit of this psi, or maybe more generally everything that it degenerates to. Then you have some quantum state phi. You normalize it, so why not? And then you look at the one particle reduced density matrices, right? Phi 1, phi 2, phi 3, and you just average the local entropies. Okay, that's the function. We like to call them quantum functionals. So these are the quantum functionals. All right, so it's like the phenomenon entropy of the reduced density matrices. And now I'm out of blackboard space. Oh, I can't move it up?
No. Right again.
So anyway, what should I do? Should I bring it down and write it again, the definition? Maybe that's the easiest, no? Maybe I leave the title to explain to you later how these things are related to this. Maybe let me. Okay, so it's clear. Our result is now that these functions that I just. Okay, fine. I'll define them again. Okay, so I'm going to define them again in this way, and then I'm going to. Okay, local reduced density matrix of this phi, and then theta 2. Okay, now, right, but so this reduced density matrix, the phenomenon entropy of this here, right, that's just the Shannon entropy of the eigenvalues. Let me call it R1. Right, and this here is also just the Shannon entropy. I'm even using the same notation, right, of the eigenvalues. Okay, so, and I'm just maximizing over all possible triples of eigenvalues. So you see the infimum here goes over all the possible, I mean, I'm looking at all the possible triples of sets of eigenvalues that I could reach from psi by slog, okay? And actually, I had been working on that previously, so basically there is a theorem that tells you actually that these sets of triples of eigenvalues, that they themselves form a convex polytope. So if you, for instance, I'm going to do this by example, if you're interested in the GHZ state and what you can get out of the GHZ state, then it turns out that the possible triples of eigenvalues are given by this geometric object here, where if I take 2 qubits, right, I'm just plotting, instead of here the eigenvalues for 2 qubits, they're of course just the biggest one and the smallest one, right? So if I, for 3 qubits, want to plot this, I just plot each time the biggest one, because they sum up to 1. Right? So I have like, this is like R max of 1 on one axis, on the second axis of 2, and this here is R max of 3, say, right? And so it turns out that we have this little this little geometric object where the top corner here corresponds to the reduced density matrix eigenvalues of the product state. Right? If I take a product state, the eigenvalues are 1, 0, 1, 0, 1, 0 for the local reduced density matrices. Right? Because if I have 0 tensor 0 tensor 0, right, the local reduced density matrix, we project onto 0. That's a singular matrix. It has eigenvalues 1 and 0. If I plot the largest one, then it will be like 1 for the first, 1 for the second, 1 for the third. Right? Now think of an EPR pair tensor 0, which we also had. Maybe it's still over there. You see, it's like 0 tensor and then an EPR pair. So the local reduced eigenvalue of particle A will be 1, and the others will be a half, right? I'm normalizing it properly. So this actually gives me this point here. And the other points, those ones, they're here and here, the other two EPR pairs. And then the GHZ state, I'm going to put it here, okay? So my origin is at a half, a half, a half. Sorry, I'm not saying that before. Okay, so the GHZ state, of course, has maximally mixed local reduced density matrix. So its maximal eigenvalue is a half, and a half for the three marginals. So that maps to here. And now you can guess where the W goes. The W actually goes in the middle of this plane spanned by the three images of the GHZ, of the EPR pair. Okay? So we like to call these entanglement polytopes. So to every slug class, right, or to every tensor here, to every psi here, I can ask myself what are the possible triples of eigenvalues of reduced density matrices, and if I have the GHZ state, then it's the entire thing that I drew here. If it's the W state, it's just this upper pyramid. If it's the EPR state, it's this one here for that state, this one here for this one, and this one for here. And of course, the SLOCC orbit of the product state is this here, which is also a convex polytope. Okay, so these are the areas. I mean, is that roughly, is that okay? Okay, so for every tensor, okay, for every tensor psi, I'm going to look at what can I get out of as local reduced density matrices. Surprisingly, they form a polytope. This is joint work with Michael Walter, Brent Doran, David Gross, and simultaneously by Kush, Savitsky, and Osmaniec. They're polytopes due to a theorem by Briand. And this thing here just minimizes, I mean, or it, sorry, that was of course max. Did I say min? Did I do it before wrong as well? Okay, I want the largest entropy, right? Sorry for this. So I'm looking at those and I'm maximizing the entropy. Okay? What's the maximum entropy? If I start with the GHZ state, what's the maximum average local entropy that I can get? Think of this theta as being a third, a third, and a third. All right? Well, it's going to be the GHZ itself. All right? That's the maximum local entropy I can get out of the GHZ. So it will, when I carry out this maximization here, for any point in the GHZ class, I'll get this guy here as the maximizer, and I'll get a value of 1 for this entropy. If I take the W state here, actually this is already its closest entropy point. So actually the W here will not go further down. So I'm kind of like stuck here with my minimization. If I take this one, it's this, and so on. And so we can make a little table. Maybe we can make this table in, I can make a little table for the W's and for the GHZ of what the values are that one gets. All right. So if we, for instance, take a third, and a third, right, as our weighting, and we plug in the GHZ, we get 1. If we plug in the W, we get actually the binary entropy of a third, which is 0.92, I think. And if you take the EPR state here, I think it's 2/3. And if you take the product state, then you get 0. Okay? So one can compute these functionals, and what they now tell us is that even under asymptotic restriction, the W cannot be converted into a GHZ. Okay, so the consequence, okay, so, well, maybe yeah. So my point is, of course, that these E theta here are examples of functions that are additive monotones in the Strassen sense, and they're also normalized. We actually see here that it's normalized, this one. And you see that now, because this value is lower, it will prohibit this, right? So this transformation is not possible, okay, for instance. And likewise, this is smaller than this, thus this transformation is not possible. Yeah, for the MAMU, so all our functionals, they restrict on tight tensors to Strassen's functionals. And Strassen computed his functionals for this, yes. So for, yeah, it's 2, yeah. Yeah, so it's, the lowest point is 2, right?
So you have use that to disprove, like.
Sorry?
You cannot use this to show that omega is like strictly bigger than 2. That's not.
No, you cannot use this technique to show that omega is strictly bigger than 2. Well, in principle you can, right? If you find new monotones, but all of Strassen's are also, everything is consistent with the possibility that the entanglement cost is equal to the maximum local dimension, or to the local dimension, say.
Right.
So everything is consistent with that. It could be, it's a generalization of the omega equal 2 conjecture. All right, I was going to say something about the proof. Maybe a couple of words about it. Is it clear? Are you happy with this? Are there any questions?
Yeah. I mean, for Neumann is very unnatural for its log, right? Of course, you have supreme, and so that's why.
Yeah, but that's important.
Do you need for Neumann, or can be like some other function?
No, I think the phenomenon is important here. Well, maybe you can come up with other functions, but the phenomenon is important. You see, the soup does make it non-phenomenon-y.
Yes.
Right? Because basically you do the same, like in information theory, expand it into type classes, but then you have to optimize over which type to take, because it's not you don't have a natural probability weighting on the type, and therefore you get this soup. Okay. In Strassen's functionals, it's even more obvious. In Strassen's functional, it's really obvious that the way it's constructed, that he goes for the types, and then in the types he has to maximize over the type and so on.
But if you don't have the average, why you get phenomenon?
Sorry?
You don't take this average over the types, why you get phenomenon?
No, the phenomenon is it's just the entry level. We can talk maybe more about it later. Yeah. So, but anyway, what makes this thing additive is so one direction, of course, is. One direction, of course, is easy to see, namely that is the direction that the tensor product, applied to the tensor product, is defined as a supremum, right? So one direction is obvious, and the other direction, one has to use a different characterization of this polytope here via invariant functions due to Briand, and we use this characterization together with some observation about something called the Kronecker coefficients. From some time ago, such that we can handle, such that we get also an upper bound and thereby an equality condition for them. So I think I'm kind of running out of time. I could tell you that this has applications and is related to recent work on the CAPSAT problem and additive combinatorics and something called slice rank. And what I kind of like about this work, like personally, is that when I first looked at these polytopes, it was not clear to me that they have any asymptotic meaning. It just looked like it tells me something about restriction, about slot classification, but it didn't see that this should have asymptotic meaning. And so another way of interpreting these functionals is to say, well, we found distance measures on this polytope here that are additive under taking tensor power. distance measures for this here to the origin. So you might think of this like as a relative entropy distance. You might reinterpret this as a relative entropy distance to the origin. And so these additive distance measures, I think this is very interesting from hopefully also for algebraic geometry. But with that, let me conclude.
You could do distance to some other point?
No, we can't. Well, no, we can't. We haven't found additive distances. But of course, yeah, that would be nice if one could come up with more.